again for my second explanation on transition theory with the length relationship to derive the Erying and Ponyali equation in 1935. If we have in 1896 the Svante-Arrhenius equation that states that the reaction rate constant is directly proportional to the temperature of many physical and chemical reactions, we have also this Erying and Ponyali equation that states that or describes that the rate of chemical reaction is directly proportional to the temperature. Okay, the only difference is that in Erying equation and Ponyali equation, talking about the rate law, proportionality with the temperature, it's not the rate constant, something like that. But anyhow, we can connect that the relationship if you try to link the Arrhenius equation to the Erying and Ponyali equation later on. Okay, maybe directly proportional with each other or inversely, we don't know yet. Okay, but it is very sure that before discussing this Erying and Ponyali equation, we have now an idea of the transition theory. I discussed that a while ago, right, in the first segment of vlogging. Okay, so we need to derive now an equation for that. Again, we need to have the energy diagram. Again, delta gives free energy in the y-axis. Okay, you have to take note, guys, that in Ponyali and Erying equation, the graph is always plotted by the gives free energy and the reaction rate. Okay, the same thing with transition state theory explanation, something like that. Okay, I have here like this. Basically, have same principle with Arrhenius. Okay, but this is a little bit more complicated, but not very complicated. Little complicated compared to Arrhenius, and this is more effective. And the Arrhenius was a little bit superseded with this theory and concepts of Erying and Ponyali equation in 1935. So if we try to subtract 1896 to 1935, 1936. 1936 minus 1896. Okay, it took 40 years from Arrhenius equation to discover the similarity that is a little bit effective compared to Arrhenius equation. Imagine 40 years. Can we survive that? Scientific research and study only 40 years. Siguro mamatay na tang tanan. We will be dying. We will just pass. For example, I am a graduate. My college years, it took me to 22 or let's say 21 years old to graduate. And I will talk 40 years. So 21 plus 40, 61 years. And that's the time I will make this equation. It took a very long time. So that means scientific research is not easy as what others think. So there's a lot of trial and error method happening there. Repeat the experiment again, repeat the data results again, gather data, let observe again, test it again, something like that. It took a lot of years. Oh my gosh, right? So maybe this Arrhenius already died. Okay, before this, Ponyali and Erying equation arrived in 1935 for this discovery of this transition state theory-based equation. Okay? Like that. Okay, it's gonna be like that. Okay, so like this. So delta G gives free energy, and let's again put this a reaction rate, Rxn as our symbol. Okay, to make it easier to be simplified, Rxn means reaction rate. Okay, again, the same graph because we used the same energy diagram previously and now it's just similar. Okay, so favored to the products, meaning spontaneous, negative, delta H or enthalpy, something like that. Okay, exothermic reaction. Okay, so it's gonna be like this, like this, like this. But this time, since we are doing the derivation of Erying and Ponyali equation, we need to be specific on our variables in the reactants. Let's put na talaga siya, which is A plus B. Okay, this is bimolecular because there are two reactants, bimolecular reaction, right? To produce product somewhere along here. Guys, I did not specify the products because for the reason there's a lot of chemical reactions involved in between in the transition state and we don't know what are the specific products to be produced here. Just like that, that's the concept for that. Actually, you can put A plus B equals to AB directly, but in this manner, I should have put specific because we don't know yet, because there's a lot of unstable intermediate reactions somewhere along in between the chemical reaction before reactants will produce two products in the completion of the chemical reaction. So that's the main purpose of it, okay? But if we try to have in one-step chemical reaction, then we can have it as A plus B is equals to AB. But for this discussion purpose, we don't have to do that. Let's put AB as products. And we don't know yet for the purpose of deriving only the equation of Erying, Henry Erying, and Michael Ponyali in 1935. Ganon. Again, we need to project an imaginary horizontal line. Okay. Same thing as what we did previously. Okay, like this, like this, like this, like this. Okay. And then transition state will be here. And activation energy will be here. But in here, guys, since we are not concerned with the transition state theory discussion, we are concerned with the equation, we don't have to put that here, the transition state, activation energy. Instead of putting the delta gives free energy. Okay, like this. Integer, we introduce another variable in between the chemical reaction that is gives free energy double integer. Wow. Okay, there's free double integer. This is not the standard gives free energy at 25 degrees Celsius and 298 Kelvin. This is delta G double integer in transition state chemical reactions unstable with unstable intermediate chemical reactions, something like that. It's gonna be like this. Okay, now guys, we need to illustrate the rate reaction constant for this, okay, to solve for the K, because it's very important, the reaction rate constants in solving or producing or deriving the Erying and Ponyali equation. Now we have three here. The first K will be the total completion of the chemical reaction in one-step chemical reaction. We can say that it's only the regular K, the small k, okay, which is, okay, this one, K, rate constant, okay, at one-step chemical reaction that we studied before in chemical kinetics. Okay, rate constant. Okay, so this is gonna be K lang siya. Okay, so I have to draw that here, putting the arrow. So it's gonna be starting from the reactant going to the product. So it's gonna be like this, K. Ganon. Okay, this is K, the entire rate constant, K. Okay, in producing A plus B two products. Okay, that's a long K. Starting from reactant going to the product. So it's going to be like that. So if we have a rate constant K from AB going to the product, so we have also a corresponding rate law or rate of chemical reaction. That's equivalent to R is equals to K. And this time, guys, we need to specify na siya because in chemical reaction kinetics, we need to specify the reactants. It's not products only because products is hypothetical. Okay, since we need to be specific na siya, then we need to put A and B. Concentration of A and B like this. Reactant. Okay, of course, reactant talaga siya, di ba? Di ba siya product? Okay, so A plus B. A rate law of this entire process of the rate, chemical reaction rate from A plus B going to the products. We have a rate constant K also, and a rate law of K, concentration of A times concentration of B, assuming that the reaction order is not our point of interest here. Assuming We don't have to recognize that yet for the purpose of discussion. Okay, theoretically and technically. Because normally it will start with 1 talaga siya. Okay? And then, from here guys, A plus B to at the half of the transition state. This is the transition state. I have to label na lang, okay? So that we will not be confused. Okay. Transition state. Ganon. Okay, guys. Now, guys, if we have a delta G double integer, automatically we have also a product A B double integer indirectly proportional to the gibbs free. Okay, because they are in the same point or region, directly proportional, in equilibrium with each other, obeying the law of conservation of matter in chemistry lecture. Chararat. Okay, so we need to put this as, in this point of transition state, we have to put this as open and close parentheses, A, B, double integer. Ganon. So now we also put K here from AB going to the reactants double integer, something like that, okay? So this is now our reactant, right? Reactant. So our reactant now will be, okay, in here. So how can we do that? So our K, this is our K, let's say 1, K1. Representation on the K1. So this here from here to here. Okay? Like that. And that is K1 here. And our K2 will be on the opposite side. K1 in going here, that produces A, B, integer, our product. But this K1, guys, it's not our interest because we don't need to produce this AB again. We need to produce the double integer. So we use the other K1 on the other side, going here. So we'll be now K2. Here, going here to the products will be the K2. So K2, okay? Here, K2, okay, like this, K2. So the K2 now will be R is equals to K. This is double integer na siya because our reactants have double integer. So this is the rate law will be K double integer. And you will ask me, Sir Sotero, why the R you did not put double integer? Because it doesn't be affected in somewhere along the reaction because we treat that in equilibrium stage. So the rate law of each case, the rate law of each reaction constant or chemical rate constant is just the same somewhere along the way by obeying the law of conservation of matter in chemistry. Okay? So it should be applied to theory. So let's say K1 is equals to K2 is equals to K3. So rate 1 is equals to rate 2 is equals to rate 3. So that's really the technique and strategy so that we can simplify equations somewhere along the way. Okay, if there's no equilibrium stage, then problem. There's a lot of variables and it seems to be complicated and we cannot derive a simplified equation after all. Okay, it's gonna be like that. So, our R, let's say have R2 because you have the K2, so R2 lang. Or pwede rin siya wala. Let's just emphasize later, okay? So, R is equals to K, double integer, and then it's gonna be A, B, double integer also. In K2, I explained. K2 from the transition state to that has an initial reactant of A, B double integer going to here in the product, so this is our K2. So our rate law will be the concentration of A, B double integer, right? Rate law, the K double integer times A, B double integer. Okay, now, so there are 3 here. Okay, our concern is 3 here. Okay, the K1 is not our concern. Okay, like that. So, we need the first equilibrium here. Here. From AB to the AB integer. This is the stage class that we have a reversible chemical reaction, equilibrium stage. The K here is not the same with the other Ks. because this is special meeting the equilibrium principle in solubility product constant in phase equilibria in chemical lecture again. Chemistry lecture again. If you remember the topic of phase equilibria or the solubility product constant principle, we have the K there. But here, introduce the K double integer instead of the regular rate constant K, in which the concentration of the products over the concentration of the reactant. Remember? So we put the big K. Okay. Actually, guys, it depends on you if you put a big K. It's up to you what you will designate. Okay. Just understand how the way it is being presented. Okay. So this is the a capital K, double integer. Why I put double integer? Because our products have double integer somewhere in the transition state. That's the purpose lang. Para we should have an agreement. So if we put double integer superscript with reactants, we also put double integer superscript with a rate constant. But this time, our rate constant starting from AB to the transition state will now be equal to big K double integer equal to, okay, big K double integer is equals to the concentration of the products, which is AB double integer over the concentration of A and B, which is the equilibrium constant supposedly in chemistry lecture. Okay, capital K double integer, which have an reversible chemical reaction. I'll put arrow like that. Symbol of arrow of reversible chemical reaction is like this in chemistry. Like an arrow going to the right, going to the left, like this. Irreversible, like this. Arrow going to the right, to the products, arrow going to the reactant, meaning it can be converted backward or forward. It will just have the same rate. That's why it's equilibrium constant. Okay. K equilibrium constant at double integer because our products have double integer AB. Okay, ganun siya. So, what else for this? Okay. It's gonna be like this. And now we have the rate constant regular. It's here, right? Now we group all the R. Okay, group all the R. The R in going to the AB integer to the products. The R here, this is, let's say this is the 0.3. Somewhere here, the 0.3. Okay, and we have also the R, K double integer going to AB, which is the K2. Okay, this is the 2. The 2, guys, is transition state going to the products only. Transition 2 going to the products, and this is our 2. Our 3 is the AB here going to the products. This is the overall one state chemical reaction. So 2, 3, and our here we cannot designate this as 1, but instead we will designate this as another. Let's say, ano lang siya, let's say, I. It depends kasi whatever you will designate, right? So I will just put I. Okay, from here to here, equilibrium, okay, stage. So I just put from here to here, our rate flow here will be equal to I. Okay? So I is the rate low or rate of chemical reaction from A plus B to A plus B integer, and it's designated as I. And our 2 will be from the overall AB reactant going to the products all throughout one complete chemical reaction. And our 3 is gonna be the integer only from the center to here. 2 is only here, and the 3 is the overall from A plus B going to here, and the 2 is in the transition state AB double integer going to the products. Okay, something like that. Now, applying the law of conservation of matter in chemistry, equilibrium stage, assuming it obeys the steady state flow. Now we need to equate the points the points I, the points 2, and the points 3. Okay, to derive an equation of the Erying and Ponyali equation. Okay, that's our main goal here. Okay, like that. Okay, if I have a whiteboard, you can easily understand, but I have only got paper, so you cannot easily understand what I am emphasizing for. Okay, but anyhow, it's just manageable, right? Okay, now, so, okay, at point 3, the overall, okay, at point 3, which is equal to the R only. So R is equal to at point 2, which is from the transition state double integrate to the products, we have R also. Anyhow, there's a pointsman. So 2 is equals to R, like this. And then at point I is equals to Ri. This is at point I. This is now our law of conservation of matter. At point 2, R, at point 3, R again. But anyhow, it's understood that there's a rate law specific formula for R. It doesn't matter. Okay? And then the I will be the Ri. Equate these two and substitute the values of each rate constant, something like that. Okay. R from 3, we have, look at the graph, like this. So we have R is equal to Ka times B. Concentration again. So put that here. Ganon. So K, A, B. And then in the points 2, what's the value of points 2 from the transition state AB double anti-gear going to the products? What is the R here? Okay, the 2 will be K double anti-gear. Okay. Then AB concentration double anti-gear, like that. And equal also to the I here, which is the equilibrium constant, which is the unique, not the same with the other rate law. This will be now become the concentration of the products, AB anti-gear, over the initial concentration AB here. Okay, put that here. So, okay, like this. Guys, since there's no rate here, okay, how can you do that? There's no rate here. How can you do that? Okay, just put K is equals to double anti-gear is equals to AB, because the rate law here is not the concern in this topic of chemical equilibrium, right? Only the rate constant. Okay, so just let this as special in your I points here. Actually, if you can also force to do that, it could still also have the R, K double integral like this, but we are not sure really. Maybe I will fail in my discussion because it is not really part of my research and my review, and my stock knowledge doesn't dictates for that validity. So if we try maybe, but just as is the equation of this K equilibrium constant at transition state from AB to AB integer. Okay, like this. Okay, now since this special is the only different, we don't have to equate this here because you will be confused. There's no K here, so you will force to equate 2 and 3 here. 2 and 3. So what do you notice here? What do you notice here from this equation? Okay, so it's either you're gonna solve for the value of AB integer or K, any one of the quantities, and after that substitute that to the special equilibrium constant at transition state at double integer. Let's do mathematics na talaga siya. Basic mathematics, direct substitution after rearranging this two equations in equilibrium stage equation. Okay, we equate this one, right? This equality sign. Now solve for, let's say, it's up to us, now according to your comfortability. And now I will solve for let's say K, like that, or I will solve for AB integer. Any quantity you want to choose, it will just be okay. Somewhere along the way it will be simplified. But here I will choose the AB integer to find out, and then the value of AB integer I will substitute that in the special equilibrium K here. Okay, let's try. Okay, so this one is gonna be, so solving for k double integer, small k double integer siya ha, sa point 2, is equals to, like this, so k, a, b, a, b double integer. Okay, like that. This is the big K, so that we will not be confused. Let's emphasize this. This special equilibrium rate constant double integer is the big K, and the small k is this one, so that we will not be confused because we are using the K. Okay, something like that. So if we solve the small k double integer, we obtain this value. Okay, like this, AB. Okay, like that. Okay, like that. So we solve na that one. So let's try individually. So solve for k also. So k is equals to AB. Okay, AB. The k constant at point 3, isolve mo siya. So still k double integer, small letter double integer. Okay, that is AB double integer over AB. Okay, like this. Okay, like this. So this is the k here. The k, a, b double integer over a b. Okay, something like that. Now solve for the value of a, b integer. We'll just solve this one by one because we are not really sure what is really the quantity to be substituted there to obtain a simplified answer. Anyway, you can try naman talaga siya. Okay? Any tries you want. Okay? Because I did not practice. Okay? So I have to choose four ways. Okay? So we need to choose for the AB integer first. So AB integer first, we have double integer is equals to the k, okay, AB, okay, over k double integer. So this is equation number 2. Let's assume equation number 1, equation 2, equation 3, so that we can use that in a proper way. So equation 1, equation 2, equation 3. And now we still use another equation because we have 4 quantities here to be equated. We have at least 4 quantities to find out. So the last will be the AB concentration is equal to, okay, k integer a, b double integer over like k. This is equation number 4. Okay, ganon. Now observe guys, which of among the 4 are very easy to substitute in the special equilibrium constant reaction at point I, at Ri. So which is the most convenient? In a way, all can be accepted, but we need to use the most easy and convenient to substitute. Where? So let's investigate visualization. Okay, it could be the 1. If it is the 1, so it's very difficult because it reversed. Okay, it will take time for us to do that. 2 also, then like this. Okay, it can be something like that. So 3. So A, B, K, AB, K integer, 4AB, KAB, integer K. I'd rather use 3 because the 3 guys is very easy, really. Okay, it's very easy to do that here. Okay, here 2 and 3 is the possible one. 2 and 3 is okay to use because the 2 also the same form with this, and the 3 also we solve for the AB integer and substitute that here. Then it will be simplified. Let's try 3. I love 3. Okay, charot lang, oy. Okay, so we need to substitute. Okay. Okay, it's gonna be like that. So big K, which is the equilibrium constant at transition state to produce a B integer product. Okay, so big K is equal to this one, big K. We use this one, we use this formula. This one we will use for check. Okay, we use this. And apply number 3. This one. Substitute that here. Okay, it's gonna be like this. Okay. A B integer is equals to small k. Okay. A B. Okay. A B. So like this. And then over k double integer. Okay. Over AB. Okay. Like that. This is the resulting equation. This one. K, big K, capital double integer is equal to the concentration of AB. Okay. Times K over the small letter K double integer over the concentrations of A and B. So what do you notice here, class, is very identifiable and easy to distinguish. The concentrations A and B will be cancelled out directly if we choose this equation 3 here to substitute in our special equation of the equilibrium constant at transition state. Meaning, equilibrium stage, arrow going to the product and arrow going to the left. If there's no like this, you don't have to put in equilibrium for this. And you will never use this special case equals to the concentration of the product over the concentration of the reactant. Okay? Take note also the applicability of the theory and principle. You have to think before doing the mathematical operation. Okay? Something like that. And you have to cancel the A and B here. Like this. And then what will be left? Capital K double integer is equals to K small k over K double integer. This one. Oh my goodness. Cancels out concentration. So K is equals to the small k over the K double integer in the denominator. So rearrange the equation. So for the, let's say the K, the regular K, because that is the K from point 3. Okay? That is the K for point 3. In going from the reactant going to the products, that is the K we are interested for because that is the complete reaction in the entire process of your chemical reaction. So we need to consider the K here. This is the K here at point 3 in the graphical representation of our energy diagram. So we need to solve for K, basic algebra. Okay, so cross multiplication. So this gonna be, so K is equals to the big K double integer times small k double integer. This is gonna be our final equation. Oh my goodness, so amazing. We have a 3K somewhere in the end. We have the rate constant, the complete chemical reaction throughout the process is equal to the capital K double integer in the transition state to produce an AB double integer product times the small letter K double integer, okay, at point 2, okay, to produce a product and a reactant with AB double integer. Okay, something like that. So, guys, in this situation alone, what can you notice? All are K's. Again, you need to understand each formula of this case. In chemistry lecture, linked with physical chemistry, it's gonna be like that always. Lecture is the basic foundation. And then we get that there to be used in physical chemistry and thermodynamics. And then we can use that both in linking to chemical reaction kinetics. Guys, chemical reaction kinetics and chemical reaction engineering is the heart of chemical engineering. Heart. Just like a cement plant, the heart of the cement plant is the kiln area. K-I-L-N. Okay, so we should establish which is the heart of that study. So the heart of the study of chemical engineering, according to George Davis as a father of chemical engineering, the heart of the study is not unit operations, it's not unit processes, it's not CHE calculation, but it is chemical reaction engineering or chemical reaction kinetics. Example, chemical reactors. Okay, like that, to produce chemical reactors. Something like that. Because it's in there that we need to know how fast and slow the chemical reaction really is, which is really the total application of an engineering course. Mathematics, science, technology. Because if you talk about unit processes, not too much with this chemical, sometimes not employed. Okay, and then if you talk about thermodynamics, it's not concerned with what's happening in the in between of the chemical reaction. It's concerned only in the initial state and the final state, and in between we don't know what's going on, right? Like that. So it's the chemical kinetics, this topic really. Okay, so if we can understand really for this, and then we have equipped with new technology, and your work is in the field really, then you can work in a chemical reactor to design a chemical reactor. Okay, like that. If your job is in that real world of chemical reaction engineering, so you will be assigned in as a process engineer in designing a chemical reactors. Okay, like that. So this one, so K. So what is K? This is the rate constant of the entire chemical process. Okay, and then big K. This is where the Boltzmann constant appeared that I discussed to you a while ago. That's why I discussed the Boltzmann constant. How do we derive that one? Because we need that here in the transition state equation of Erying and Ponyali equation in 1935. Right? So big K double integer is equal to, okay, Boltzmann constant. KB, we already memorized that value, right? Because we derived that a while ago. Okay, times capital T, the temperature in Kelvin, over the H, which is the Planck constant. Here. This is the KB double integer. Okay. The temperature T, capital T, times the Boltzmann constant over the H. The Boltzmann constant, guys, is, we memorized that already, 1.38 times 10 to the negative 23 joules per Kelvin. And then our H Planck constant, okay, just write down in a sheet of paper or register that in your brain cells. The value of the Planck constant is 6.63 times 10 to the negative 34. But this time, the unit is joules times second. Okay, like that. So you have to substitute that here in your final equation. Here. Okay. Now, since there is also small k double integer, the small k double integer is related to Arrhenius theory. If we have the Arrhenius, which is equal to the rate constant k, is equal to the pre-exponential factor times exponential negative activation energy over the universal gas constant and capital T, we have also the k double integer is equal to the exponential of, instead of activation energy, the Gibbs free energy double integer over RT, in which we discussed in our graph. It's here. G double integer na siya. Dili na siya ang activation energy. That's what I told you. It's basically similar with Arrhenius. Okay? And this is more, a little bit accurate to Arrhenius. Namatay na lang si Arrhenius. Okay? And then, another scientific theory follows. But it doesn't mean the theory of Arrhenius was neglected. In fact, it's been used by Erying and Ponyali. It has been modified, but the basic concepts and theories was still obtained by Arhenius equation. So this Ponyali and Erying will be thankful to Mr. Arrhenius. Okay? Because without Arrhenius, they cannot formulate this theory of this equation of transition state theory regarding the chemical rate reaction dependency or directly proportional to the temperature. Okay, something like that. So, okay, small k double integer is equal to the exponential negative delta G double integer over RT. Now substitute these two equations in our case, triple case final derived equation. Substitute here. Okay, substitute the top. So small letter k as the rate constant in the entire chemical process, the entire chemical reaction is equal to the capital K, the equilibrium constant in a transition state is equal to, close and open parenthesis, Boltzmann constant, capital T over the Planck's constant, okay, times the exponential negative delta G over RT. Then bingo, we have a general equation of Erying and Ponyali equation. This one we derive now. If you go to certain different books and different sources in online or whatever, chuba chucho, you can also obtain like this formula, the same as what we did now. Okay? Like that. But the only difference based on my research, there's a transmission coefficient. But it doesn't affect really in the formula because it is more on the ideal behavior. So it designated as 1. The transmission coefficient somewhere besides the coefficient of this here. Beside the, beside the Boltzmann. Or beside this KB. Okay, here. Okay, like this. K double integral B. But the one transmission coefficient will just be irrelevant because there's only one, right? If you multiply to certain one, it's the same value. So it doesn't matter at all. Just like the ideal gas law, if you multiply this with 1 mole, then 1 is just a 1. It never change your figure at all. Right? The same theory and principle behind this. That's why it is very valid and logical and technical to eliminate directly the transmission coefficient beside this capital K double integer equilibrium constant formula. Okay, I'm just telling you that there's a transmission coefficient. Maybe the question in the future examination or board examination will say, what is the value of transmission coefficient in the equilibrium constant value of the Boltzmann constant? A, 1, B, 2, C, 3, D, none of the above. If you don't have an idea, okay, it is 1, the transmission coefficient. Okay, that's why the eliminated directly, it seems to be irrelevant at all. Because anything will be multiplied by 1, the numerical figure is still 1. It's still the same, that value will be able to multiply. Okay, something like that. And in chemistry, putting 1 or no putting 1 is just the same as 1. Okay, remember that one, right? So like that. Okay, so this is the final. So I have to stress out transmission coefficient. The K there, this is very ironic. The K there is somewhat slight just to have a difference between these 3 Ks. We have 4 Ks na talaga, di ba? We have the capital K double integer, the small K double integer, and the small letter K. And we have also the letter K, which is the transmission coefficient. K pa rin siya. And then it slightly bend just to distinguish that this is gonna be the transmission coefficient equal to 1. Okay, like this. I will put this. Katawanan kayo siya nga K. Ganon. Murag nalupag siya nga K. Or distorted rate constant K. This is the transmission coefficient equal to 1. Okay? Like this. Then if the question also in the examination in the future, for example, in the Erying equation, in Erying and Ponyali equation, true or false, transmission coefficient is relevant or not? A, true, B, false, B, both, C, none of the above. So, irrelevant. That's why it's not being carried in your formula. Okay? So, the answer will be false, something like that, because that's irrelevant. Or negligible, because too small to consider that does not affect the value of your rate constant if you compute and substitute values in your different quantities involved. Something like that, okay? So gonna be, this is general pa yun siya, guys. General. We need to express this in an algebra point of view or in a calculus point of view. So simultaneously. So we can do that by graphing the ln of the small rate constant versus the temperature again. Same what Arhenius did, but there's a lot of quantities here. Okay? Let's do now, let's graph now. I think we're gonna continue this graphical representation tomorrow because I don't have time anymore. I have to sleep now. Okay, let's do the part 2 tomorrow, in which the graphical representation between the ln K and the temperature in the x-axis, so that we can come up in terms of the slope for algebra. Y is equals to mx plus b. Y is the vertical coordinate or y coordinate, and the m and x is the x coordinate. Okay, the m is the slope and the b is the y-intercept. Okay, that's why it's called the b or the intercept only, no problem. Okay, intercept. Now the intercept the slope and the y and the x has its own equivalent quantities in here also. When you integrate or calculus and you do the algebra. And your slope also will be like this, same as Arhenius. So slope is equals to y2 minus y1 over x2 minus x1. And then you have to substitute what is y2 here in this quantities here. And what is also y1. And then what is x2 in the quantities here, what is x1 in the quantities there. Okay, and then you can solve. And then until such time you can come up to the form of y is equals to mx plus b. And your slope will be the quantities here, we don't know yet. So we need to equate again. Even in algebra, we need to equate, just like in chemistry, law of conservation of matter. So slope 1 is equals to the slope 2. The slope 1 in terms of algebra, and the slope 2 in terms of chemical reaction. That we need to point out here in the INXB form. When you equate the two slope, then bingo, you can obtain the most simplified equation of Erying and Ponyali equation in terms of the slope, the y coordinate, the x coordinate, and the intercept. Something like that. And that's the time you can graphically do that if you have series of results in experimentation in the laboratory. So that you can grab that there, blah blah blah, so and so, and then you can compute one by one based on your plotting. Okay, and then you can get what type of curve you'll be able to achieve, something like that. Because here is theoretical only, we don't have the experimental to do this one by one. Okay, but experimentation will take how many mass to produce the curve, right? To project a curve, guys, it's not easy. There's a lot of points for that. Okay, this is only for the purpose of discussion. Okay, and we are not inside the laboratory to do this experimentally. Okay, so we are now having the explanations and discussion for the basic foundation on how to derive Erying and Ponyali equation in 1935. Thank you so much! That's all. Any questions so far? Okay, in my derivation. Okay, it took me 3 papers to present this discussion, right? See. But when I have the whiteboard in the future, I could deliver my discussion very well, rather than this. Okay, so thank you so much for watching this live stream. And then if you are going to comment, then you can do it. Comment down below in the comment section. And then you can subscribe to the YT channel if you are not subscribing yet. And then you can click the notification bell for some newest updates of the Engr Eternal Voice. Okay, because it's in there that you can receive newest updates from my content in my YT channel. Thank you so much for watching, guys. See you later. God bless everybody. Bye bye.